Hello everyone. Let's work out a few more problems today, and we will try to look at some other concepts especially related to LES in today's class. So problem number 10, let u of x have a Fourier transform of u hat of kappa so that the filtered velocity u bar has the Fourier transform u bar hat is g of hat kappa times u hat of kappa. Show that the Fourier transform of the residual u prime of x is u prime hat of kappa is the Fourier transform of u prime of x equal to 1 minus g hat of kappa times u hat of kappa. Okay, so let's see. Let's start with the first part. Okay, now, first part. If I take a Fourier transform of the residual, right? So I will have u prime hat of kappa. That is going to be equal to basically the Fourier transform of u of x, isn't it? By definition. The Fourier transform is defined as a Fourier operation applied on u of x. Okay, which is now, if I define the residual as f of the instantaneous, the random variable minus the filtered variable, isn't it? That's how it is defined by definition of LES, right? That's the filter decomposition. So then all I need to do is take f of u of x separately and f of u bar of x separately. I would like to put a flower bracket or a double bracket where I'm taking the Fourier transform. Right? So now this Fourier transform of the velocity by definition is this one here. The transfer function multiplied by u hat of kappa, isn't it? So here this essentially just becomes u hat of kappa, because that's the Fourier transform of u of x, minus here what happens is the Fourier transform of the filtered, okay, the Fourier transform of the filtered, that becomes g hat of kappa times u hat of kappa, isn't it? Here that is what is given here, g hat of kappa times u hat of kappa. Because remember, this essentially is u filtered hat of kappa, which is what this is, u filtered hat of kappa. I'm taking the Fourier transform first. I get it in Fourier space, but it's a filtered Fourier transform. Okay, so that essentially becomes g hat of kappa times u hat of kappa. And then from here, all I need to do is factor out a u hat of kappa. Then I have 1 minus g hat of kappa times u hat of kappa. Hence proved. That is the residual. Isn't it? That should be the first part. Yes. Now we need to take the filtered residual. Okay, so the filtered residual would be, so this is the second part of the question, and filtered residual is u prime bar filtered and then hat of that, a kappa, is essentially, what is it? It is g hat of kappa times u filtered of kappa. Isn't it? It's a Fourier space, right? So that is g hat of kappa times u prime. I'm sorry, it is u prime hat of kappa, which is what we just found. Okay, what is this? What you're doing is you are essentially taking the filtered residual in Fourier space. You're taking the filtered residual in Fourier space, or you're taking the filtered residual value and considering it in Fourier space, or you are taking the residual value in Fourier space and filtering it. That is what both are the same, and that is what we are doing here. Whether you take a filtering of the physical space variable and then take the Fourier transform, or whether you take the Fourier transform and then filter it, both are the same. So here what I'm doing is I'm taking g hat of kappa times u hat prime of kappa. Now u hat prime of kappa we just found out, so that would be g hat of kappa times 1 minus g hat of kappa times u hat of kappa. Hence proved, isn't it? Isn't that what we had to prove? Yes. There you go. That's the filtered residual. Now let's do a doubly filtered operation. Okay, so this is the third part. The third part is the doubly filtered variable u double bar of x. Okay, so u double bar of kappa u hat is the Fourier transform of the double filtered variable, which is g hat squared times u hat of kappa. So that's also relatively straightforward. So you have to think of it as, if you take u double filtered and hat of kappa, that would be equal to, okay, you are essentially filtering it twice. So it would be the same as g hat of kappa times u one time filtered of kappa, isn't it? And this right here is g hat of kappa squared times u hat of kappa, hence proved. Okay, remember the doubly filtered, if this filter is equal to u doubly filtered of x plus u prime filtered of x. Okay, just like u filtered is equal to ux plus u prime of x, u filtered is equal to u doubly filtered, I'm sorry, I wrote it the other way around, u of x is equal to u filtered plus u prime. So just like that, u filtered is u doubly filtered plus u prime filtered residual. So there you go. You have now proven all the three parts. I hope that is clear. Let's look at problem number 11. Okay, so problem number 11, consider high Reynolds number homogeneous isotropic turbulence and an isotropic filter of width delta and characteristic wave number of Kc equals pi over delta. The kinetic energy of the residual motions is given by K of R, right? K of R equal to Kr average is equal to 0 to infinity 1 minus G hat of kappa squared times E of kappa d kappa. Okay, E of kappa d kappa. So let's see. And the first part of the question is, for the sharp spectral filter with a cutoff Kc in the inertial subrange, use the Kolmogorov spectrum to obtain the estimate for the fraction of energy in the residual motions, which is Kr over K is 3/2 C, K kappa C times L to the negative 2/3, where the length scale is L is equal to K to the 3/2 over epsilon. That's the first part. So let's do the first part first. All right. The first part. Okay. Now what we know is that G hat of kappa by definition is equal to, and this is a sharp spectral filter as is given in the problem, so it would be 0 and 1. 0 when magnitude of kappa is less than kappa C, greater than kappa C, right? Because you are cutting it off, greater than or equal to kappa C, and magnitude of kappa is less than kappa C, it is equal to 1. That's a sharp spectral filter. So now if you consider Kr, which is the residual motions, and I'll go to the definition of Kr, which is this one right here. You are using the Kolmogorov spectrum for E of kappa. Okay, you are using the Kolmogorov spectrum. So what is happening is, remember, I have 1 minus G hat of kappa. I have 1 minus G hat of kappa squared. G hat of kappa is 1 until Kc, and after Kc it is 0. So when I take 1 minus g hat of kappa squared, I am taking everything after kappa c. I'm taking everything after kappa c. So my integral is going to go from Kc to infinity, isn't it? Because after kappa c it is 0. G hat is 0 and you are taking 1 minus that, isn't it? So when you do 1 minus 1 it becomes 0. So less than kappa c it becomes 0. That function becomes 0. Then you have the Kolmogorov spectrum, which is c epsilon to the 2/3 kappa to the minus 5/3 d kappa. This is what you have. Now if you just integrate it, what you are going to get is you only just need to integrate kappa to the minus 5/3. If you integrate it, you'll get minus 5/3 plus 1 divided by minus 5/3 plus 1. So then you will have minus 3/2, okay, c epsilon to the 2/3, because all those are constants, and then you have kappa to the minus 2/3, isn't it? Kappa to the minus 2/3 going from kappa c to infinity. So if you just plug everything in, what you will get is 3/2. The minus will go away. You will get 3/2 c epsilon to the 2/3 kappa c to the minus 2/3. That is what you will get as Kr. Now here what I'm going to do is, so I'm not done yet, right? I need to get the ratio of the residual kinetic energy to the total kinetic energy. But I will use this particular definition of the integral length scale, which is k to the 3/2 over epsilon, okay, k to the 3/2 over epsilon. So then what I have is kr over k, isn't it? Kr over k, okay. So then I will have 3/2, okay. So then I'll have 3/2, and I will use the definition of L. Where is it? Yeah, L is equal to k to the 3/2 over epsilon. So instead of epsilon, I can write it as k to the 3/2 over L. So I will have c times instead of epsilon, I'll have k to the 3/2 over L. So that is L to the 3/2, this whole thing raised to 2/3, and then kc to the minus 2/3, isn't it? So k to the 3/2 and 2/3, it becomes k, and then you will have L to the 3/2, so that will become kc. So then essentially what you're going to get is 3/2 c kappa c L to the, you will get L to the 2/3 minus 2/3. Kappa c L to the minus 2/3, isn't it? I am using that k, okay. So this is what I do. This is kr, okay, and this is kr over k, because there's going to be a k from here. There's going to be a k from here, which I bring it to the denominator on the left hand side. Then I have L to the minus 1 from here. L to the minus 1, L to the minus 1 from there raised to 2/3 becomes L to the negative 2/3, and that goes in here. And there you go. I think I have proven it, right? That is what I had to prove. 3/2 c kappa c L to the negative 2/3, and that's what I have. So that's your first part. Let's look at what the second part is. Show that 80% of the energy is resolved, as in kr over k is 0.2, if kappa c is chosen by this. Okay, let's see how to work that out. So the second part, okay, is I want to see now kr over k, as I had proved it earlier, is 3/2 c kappa c L to the minus 2/3. Now what I know is this is equal to 0.2, because kr over k is 0.2, only 20% is unresolved, right? So now if this is 0.2, c is 1.5, according to the Kolmogorov spectrum, it's a universal value, and then if I plug all that in, okay, I will get KCL, okay, to the minus 2/3 is 0.2 times 2 divided by 3 times 1.5. Okay, so then if I solve for this, I get KCL approximately equal to 38. Hence proved. Okay, I can easily show that. That's just algebra, right? So that's your second part. And my third part, okay, using the relations LEI is equal to 1/6 L11 and L11 is equal to 0.43 L, show that the corresponding filter width is this much. Okay, let's see how to work that out. So here what I do is, if LEI is equal to 0.43 over 6L, how do I get that? Because I have been given these two relationships. So instead of L11, I put in 0.43L, and then I get LEI is equal to 0.43 over 6L for high Reynolds number turbulence, and I know kappa C is pi over delta, right, by definition. So if I want to do delta over LEI, okay, if I want to do just delta over LEI, I just use these two relationships and I will get delta over LEI is 6 pi over 0.43, and then there will be a kappa C and there will be an L. Isn't it? Delta over LEI. So I just basically divide these two, or in this particular case multiply these two equations, right, and then invert it. That's essentially what I get. So 6 pi over 0.43 kappa CL. And now kappa CL is approximately equal to 38. If I plug that value in, I get this value to be approximately 1.16. So delta over LEI is 1.16. Okay, and hence proved, right? That is what I had to prove. It's proved. Okay, so I hope this was clear too. One last problem, which is problem number 12. This has to do with PDFs and CDFs as well. For the exponential distribution given by this, okay, so f of v is 1 over lambda exponential minus v over lambda if v is greater than or equal to 0 and is 0 otherwise, show that is the normalization condition satisfied. Okay, the normalization condition is basically integral minus infinity to infinity. This is part 1. No? F of v dv is equal to 1. We have to prove that. Okay, so all you need to do is substitute. Okay, so you will have 0 to infinity, right, 1 over lambda, because it is going to be 0 to infinity because that is all the exponential function is defined as, exponential distribution is defined as, so that is exponential of minus v over lambda, okay, dv of course. And what do you get here? If I want to make a substitution, t is equal to minus v over lambda, then this integral just becomes, it flips, it becomes minus infinity to 0 and it becomes exponential of t dt. Okay, which is exponential of t is just exponential of t, and answer comes out to be 1 when you integrate it between 0 and minus infinity. Okay, answer comes out to be 1, hence proved. That's your first part. What is the second part? You have to show that the mean value is equal to lambda. Okay, the mean value is equal to lambda. So by definition, the mean value is integral minus infinity to infinity. In this case, it will only be 0 to infinity, but I want to write the general definition, so that is minus infinity to infinity, v of f of v dv. So using that definition, right, using that definition, what will I write? I will write it as 0 to infinity. I will write v over lambda, and I will get exponential minus v over lambda dv. Isn't it? V over lambda because it is 1 over lambda, isn't it? So v over lambda exponential minus v over lambda. Again, I make the substitution of t is equal to minus v over lambda, and then what this becomes is, this actually becomes minus infinity to 0 because I've made that substitution. I will have a negative lambda on the outside, and I'll have t exponential of t dt. I just have to integrate this by parts. We have done this multiple times, right? Previously. If you just integrate this by parts, okay, what you get is, you will get the value of lambda, and use minus infinity to 0, you will get lambda. Okay, so hence proved. That is your second part. The third part is u of n equals n factorial times lambda n, as in the nth moment. U of n, okay, so this is the third part, which is u of n is n factorial. Okay, so let's first find out what would it be. It would be 0 to infinity, because the function only exists from 0 to infinity. You would get v of n over lambda. The 1 over lambda comes because it is there in the exponential distribution, and then you have exponential of minus v over lambda dv, isn't it? Now what happens is, if you just integrate by parts, what you will get is 0 to infinity. Okay, you will actually get first times the integral of the second, right? So you will get v of n exponential minus v over lambda minus the derivative of the first one, so that is n v to the n minus 1 exponential minus v over lambda, and this is dv, integral, like this. Eventually, when you work it out, what you will get is, because what ends up happening is, here you will have n v to the n minus 1 exponential v over lambda, and then here you will get v to the n exponential minus v over lambda. So then what will end up, you will end up getting n times 0 to infinity v to the n minus 1 exponential minus v over lambda dv. This is what you end up getting, which is the same as u n times lambda times the n minus 1th moment. So you keep going, and you will have n times lambda times, n times n minus 1, isn't it? Look at where I'm going here. I have n factorial times lambda. So what I'll have is n times n minus 1 times lambda squared times u n minus 2th moment. You keep going like that, eventually you will get n factorial times lambda to the n. Hence proved. So I hope that is clear. This is just integration by parts. This is what you will get. Okay. Now for the fourth part, which is the CDF, f of v, you need to prove that it is 1 minus exponential minus v over lambda if v is greater than 0, and 0 if v is less than or equal to 0. Okay, let's see. Remember, this is the fourth part. The PDF is the derivative of the CDF, isn't it? So if you use the previous equation and just integrate it, what am I integrating? I'm just integrating this. If I just integrate this, what I'll get is f of v. If I just integrate, f of v would be integral f of v, isn't it? From 0 to v. Then what I get is f of v is equal to, I'm integrating with respect to v, okay? It is not minus infinity to infinity, because minus infinity into infinity would be the normalization condition. You're integrating from 0 to v. So you would get 0 and 1 minus exponential minus V over lambda. Okay, when V is less than 0 and when V is greater than or equal to 0. That's what you end up getting for the cumulative distribution function. All I'm doing is I am using equation 2 in the first equation that was shown. Okay, equation 20 here. All I'm doing is I'm doing using that and then equating it in there. Fifth part. What is the fifth part? The probability of u greater than or equal to a lambda is e to the minus a. All right. Let's see how to work that out. So what you need to do is, if you find out if you want to find out the probability, okay, so the probability by definition is the probability of v less than b greater than or equal to a is essentially f of b minus f of a. So if you want to find out the probability of a of lambda less than or equal to v less than infinity, then that is f of infinity minus f of a lambda. That's it. And f of infinity is basically the probability of all the values being less than infinity, which is 1, and 1 minus f of a lambda. So 1 minus f of a lambda. So all I need to do is use the equation for f of v right here, and then it becomes 1 minus exponential minus a lambda divided by lambda, isn't it? Like this. So then the lambda and lambda get cancelled, and what I end up getting is the minus and the minus become plus, and I end up getting exponential of minus a. Hence proved. So I hope that was clear. So the 5 parts, this was a relatively simple problem, exponential distribution. I did not do the integration by parts here because I am assuming you can do that on your own. So I skipped that step, but I showed you what the final answer is. You just have to integrate it by parts and you will get those answers in the previous questions, previous subparts of this question. Okay, so that is the end of this entire class, and I hope you found the turbulence class very helpful. We went through quite a few concepts related to the physics of turbulence and the modeling part of turbulence, simulating turbulence in terms of direct numerical simulation. We touched upon some concepts in the RANS approaches, especially related to the turbulent viscosity hypothesis, but we did not cover a lot of RANS methods in this particular class. But what we have done is we have looked at concepts related to scales, residuals, energy cascade, Kolmogorov scales, the energy demarcation length scales, how the energy is being distributed, and we then went on to the simulation and the modeling part. So we touched upon the DNS and the LES part and not the RANS. Finally, we have had a chance to work out a few problems, and I hope you found this interesting and helpful. Thank you all for paying attention to this class. Thank you again.